Welcome to EEE 2234 Digital Electronics Laboratory. I am Mr. Oladukun AS from the Department of Computer Engineering, Ajayi Crowther University, Oyo. Um, this is Module 1 of the video lecture series for Digital Electronics Laboratory. And this is, as the title of the course hints, this is a practical course, it's a laboratory course. And due to the current pandemic around the world, I'm sure you're well aware of this. Um, Education, tertiary educations at all levels globally is probably has definitely been put on hold, and most institutions have switched to video or online lectures as we have now, or as this lecture is the pattern which the this video lecture is following. Um, like the EEE 2232, which is the basic electrical and electronic measurements course, as the same kind of challenge we had with that course is the same challenge we have with this course, in that this course is a practical course. It's not a theoretical course, and generally practical courses don't do too well with online online teaching or video lectures, in that the whole essence of having a practical course, or what makes a practical course, a laboratory course, different from a theoretical one, is the fact that students have the opportunity to get their hands on the uh, physical implementation of concepts that are taught at in their theoretical classes. They get their hands on the physical equipment, and they run practical sessions themselves. They see actual outputs that were on pen and paper before. Now they see the actual outputs in the physical world, in the real world. So we have a real challenge here, a real challenge of the fact that um, video lectures might not be very effective for teaching laboratory courses. It's pretty effective for theoretical courses. Uh, it's probably even more effective than in a way than um, actual lectures, actual physical lectures, in that if you have a video lecture, you can always go back. You can always go back to any part of the teaching that you missed, or that you did not fully grasp at the time. But whereas in real time, if you're in a physical lecture, once a lecturer has gone through a particular concept, it's possible there might not be time, or he might not be willing to go back to a concept that he had previously stated or explained for various reasons. But in a video lecture, you can always just scroll back. You just take the video back, and you listen to the explanation that the lecturer had given before. So you can watch a video lecture over and over again, two, three, four, five, six times, um, so that the basic concept thoughts can be cemented. The only problem with video lectures is that you can't ask questions. So for theoretical courses, video lectures, online teaching is pretty effective. But for laboratory courses or practical courses like this is a big challenge, in that you don't actually get to touch or you don't get your hands, you don't have the opportunity to get your hands on the laboratory equipment and actually do the connections yourself, run experiments yourself, see the outputs yourself, see the results yourself. So it's a serious challenge. It's the same kind of challenge we had with EE 2232, and the same way we circumvented, or I circumvented that the challenge for EE 2232. It's the same way we're going to try and circumvent that challenge here. So I'll be switching to I'll be making use of a virtual laboratory basically throughout this course. This course is probably even more practically oriented than 2232. 2232 still has a lot of theoretical background in it, but 2234 is basically it's as practically oriented as any laboratory course you probably have in your throughout your course of study in electrical engineering or computer engineering. So we were making use of virtual laboratory like we did it EE2232, and hopefully by the time the whole world resumes its compulsory holiday, um, Mr. Victor and Mr. Ibekwe, Mr. Ibekwe Victor and Mr. Kode, they'll be in charge of the actual practical session. So when we resume to a normal class routines, and would our technologists from UI will run through the physical implementation of the virtual experiments we're running in this module, and hopefully if you've grasped the basic concepts of these video lectures, it won't be difficult for you to understand the physical implementation when that time comes. um, so I welcome you once again to the first video lecture of the EEE 2234 series, Digital Electronics Laboratory. And basically what we'll be doing in this practical course is, it shouldn't be too strange to you. Last semester, I'm sure you did something on gates, digital gates. You did hand gates, not gates, hand gates, all gates rather, exclusive all gates, not gates, NAND gates, things like that. So basically that's what we'll be doing in this course, EE 22334. But normally this course is supposed to be the practical equivalent of the theory that you did last semester. Basically, you're supposed to get your hands on these gates and actually run practical experiments based on the theory you did last semester. But this time around, we will still do practical sessions, but just be virtual. It won't be physical laboratory. So let's go back to let's use live wire virtual laboratory. I'm using a professional edition as usual, as I did with EEE 2232. Um, we're running virtual experiments. Um, so we could use live wire to run experiments for electrical circuits, electronic circuits. We could also use it for digital circuits. So we've used it for electrical or electronic circuits in EEE 2232. Now we'll be using it for digital circuits, circuits. So LiveWire is a robust, is a versatile virtual laboratory environment, and so let's go to our gallery. We have our gallery on the right, gallery window. We can select our various um, virtual laboratory equipment, as we did with EE2232. And but before we go deep into um, digital circuits or digital logic circuits, um, we probably need to understand first of all what a digital signal is. What is a digital signal? You know, basically in the digital world, it's all about communication. Uh, generating information digitally. You can have digital information, you can have analog information. So information is basically or signal basically is you conveying information. So you can have digital information or analog information, digital signal, analog signal. So before we go deep into digital circuits, digital conventional circuits, we need to first of all really explain or ensure that you grasp how what's a digital signal and what is an analog signal, and how do they differ from each other. So um, digital signals, I'm sure you did it you did this last semester, but we'll probably just go over it again before we dive deep into the virtual laboratory environment. Digital signals, they have just two states. A digital signal can either be a logic 1 or logic 0. That's if you are working at binary level, either logic 1 or logic 0. But the question now is, what exactly is logic 1? What is logic 0? So how does that differ from analog circuit? How does that differ from analog circuit? So let's go back to our gallery once again. You go back to the gallery and select power supplies. So from based on the power supply, we are going to actually try and differentiate um, what's how differentiate how um, analog signals differ from digital signals. We have oscilloscope. We probably make use of an oscilloscope. An oscilloscope will help us with that. We can view a digital signal. We can view an analog signal using an oscilloscope. So let's go to power supplies. So power supplies. Let me select the cell. In EE2232 we use the battery, but it's basically the same thing. Single cell battery, and the other battery that you have is a multi-cell battery. So if I connect the positive, remember that the longer terminal of your DC of your battery symbol is the positive, and the shorter one is the negative. So positive to positive and negative to negative. You're using just one channel, channel one. So click. So um, now, after connecting this, now we want to let's check. Let's hard graph so we can see the output of our oscilloscope. Right click, hard graph, and we click. So we can shift the graph around a bit. Um, the vertical axis is voltage, the horizontal axis is time. So right click, adjust the properties. You want to change the maximum. Now, a digital signal has two levels, like I said, is either logic 1 or logic 0. Logic 1 or logic 0. Now, logic 1 is analogous to 5 volts. What is logic 1? In practical sense, in the real world, logic 1 is 5 volts, and in the real world, logic 0 is 0 volts. So, you see here that with a signal of just 5 volts, you see that it's just permanently 5. 5. There's a straight line that appears 5 volts, 5 volts, 5. So that 5 volts is 1. So this source, this battery is giving us a digital signal of 1, binary value 1. So let's stop the simulation, change the properties, and 0. So 0 volts. So we want, you see here there's a straight line at the 0 volt level. So that is signal 0 volt and 5 volt. 0, 5 volt. That is digital. That's all. So in digital world, you have 5 volt and you have 0 volt. 5 volts represent logic 1 and 0 volts represent logic 0. Straight line. DC volts, 4 DC, 5 volt, 5 volt DC, and 0 volt DC. That is all you need in a digital world. There are no intermediaries. There is no 2.5 volt. There is no 3 volt. There is no. It's just 5 volts and 0 volts. That is digital. That's digital information. That's how digital information looks like. In between 0 volts, it's 0 volts. Just two values, two discrete values, 0 volts and 5 volts. And now, uh, in E2232, we went through extensively on AC voltage, and we see that in AC voltage, let's get an AC voltage source. If we replace our DC voltage with an AC voltage source, click and drag, click drag down, click in of terminal terminal, connect the positive to the positive, negative to the negative, and we right click, change the properties. RMS voltage, let's change RMS voltage. I'll try to beat to 5 volts, for example. Okay, and let's run simulation. We see there that, okay, yeah, the 5 volts RMS, so the peak voltage will actually be above 5 volts. So that is expected. We've done that in E2232. So I encourage you to probably go through E2232 video lecture first before coming here, because I won't want us to spend more time on AC voltage again, since we've done that already in E2232 module 1. So we see here that in AC voltage or AC signal, this is an analog signal. AC signals are analog signals in that you have multiple values. Here it's above 5 volts. It's, it can be negative, it can be positive, it can be 3, it can be, so there are multiple values. So AC voltage has multiple values. DC voltage just has two fixed values, 5 volts, and so rather not DC. Digital has two fixed values. It's either 5 volts or 0 volts, but AC can have infinite number of values. So let's change our properties once again, get it back to 5 volts. So in 5 volts, let's run the simulation. You can see straight line. This is digital. Digital is a straight line 5 volts, or straight line 0 volts. That is digital. But in analog, analog is AC voltage is an analog voltage. Analog voltage you can have multiple values. It's not fixed values as you have with DC. So sorry, as you have with digital. In digital, this is 0 volts for logic 0, 5 volts is logic 1. So that is how digital signals differ from analog signals. A digital signal, you can create a digital signal by having two voltage sources. If you have one 5-volt source and one 0-volt source, two voltage sources, one 5-volt source, one 0-volt source, you can create a digital signal. If you want to represent one logic 1 in digital, you use 5 volts. If you want to represent logic 0 in digital world, use 0 volts. So 5 volts for logic 1, 0 volts for logic 0. But in analog, if you want to create an analog signal, there are so many, it's so there are too many, there are infinite number of values you can generate, infinite number of values. So it's basically like an AC signal. So any value, it can be 42, it can be 30 volt, plus 42, minus 42, so that is how AC is different from DC. DC, sorry, not AC, rather. That's how digital signals differ from analog signals. So let me get a clock. I want to see if I can get another digital signal. You can generate a clock, a digital clock actually. We'll come back to that later. If I click connect it to positive and let me see if I can get a ground ground to negative. So I connect the digital clock signal to positive and the ground, I got negative. So aha, okay, yeah, this is a digital signal, but there's a fault, it's kind of fault. Let me see if I can adjust the properties. Okay, it's already the frequency I can adjust. um this is actually, this is a simulation fault. This is a bug. There's a bug in this live wire virtual environment, in that the voltage, the upper voltage for the clock should be 5 volts. I think here it is 9 volts. So it is taking 9 volts as logic 1 and 0 volt as logic 0. Logic 0 is correct, it should be 0 volts, but it's actually supposed to be logic, it's supposed to be 5 volts. 5 volts is supposed to be logic 1, not 9 volts. So you see here that it is 90909090. That's 101010101090. 9 volts, 0 volt, 9 volts, 0 volt. One logic 1, logic 0, logic 1. So it's actually supposed to be 5 volts, 0 volt, 5 volts, 0 volt. So I get that's a bug. That's a bug in this virtual laboratory. Should be 5 volts should be logic 1 and 0 volts should be logic 0, not 9 volts logic 1 and 0 volt logic 0. So I don't think this I've used Proteus extensively. This bug doesn't exist in Proteus. In Proteus, it is the correct voltage levels. It is 5 volts for logic 1 and 0 volts for logic 0. But notwithstanding, let's still continue with live wire. Just have at the back of your mind that instead of 9 volts for logic 1, it should be 5 volts for logic 1 and 0 volts for logic 0. Uh, so we see here that if you look at this the graph on the oscilloscope, um, 1, that logic 1, when it's at 9 volts, which is supposed to be 5 volts, it's 1. Then when it's at 0, it's volt is logic 0, and then like that. So let's let's clean things up. So to delete any component, you just left click on it and press delete. Left click on it and press delete. So you use that to delete any virtual instruments you want to delete. So let's get a blank table, virtual table, a blank virtual library table. So let's go to logic gates now. Logic gates. So we want to create a digital circuit. If you want to create a digital circuit, you make use of logic gates. Logic gates. Whereas if you are an electronic circuit, you use resistor, you use your filament bulb and things like that. But here we use gates like AND gates, inverter, NAND gates, OR gate, NOR gate. So this is the inverter, NAND gate, 2 input NAND gate, 4 input NAND gates, XOR gate, also exclusive OR gate. So there are so many standard gates here. So we'll start with the AND gate. Click on it and drag, click and drag and drop, click, drag, drop. So click, drag, click, that, drop. That's two inputs. This is a 2 input AND gate. 2 input AND gate. Look at the shape of the symbol. This is how an AND gate looks like, or this is how, yeah, an AND gate looks like. So click and drag, click and drag. let's see, insert text box. So there's something called truth table. um Truth table. What truth table shows us is it shows us the corresponding output for every input. So whenever the input you feed to your digital circuit, we can determine what the output will be by looking at the truth table. So the truth table gives us the behavior. The truth table shows us the behavior, help us determine the behavior of our logic circuit, of our digital circuit. So you can determine how your digital circuit will behave by drawing out the truth table. So the truth table just consists of the digital inputs and also the digital output or digital outputs. So um, so input and output basically. Okay, let's see what we can do. If we have input A and input B, so because this AND gate is a two input AND gate, it has two inputs. You can say our input is A and B, and our output is C. So A and B are inputs and C is our output. So um, now we are going to try and draw out the truth table, for our um, our mini digital circuit. You want to draw a very small, you want to construct a small digital circuit with just a single two input AND gate. So our possible inputs, now a digital signal can either be 0 or 1. So we when you create a digital circuit, actually you feed it all possible inputs. So the first possible input for this two input AND gate is for both inputs to be 0. If both inputs are 0, that's possibility 1. Second possibility is A 0 and B 1. That's the second possibility, that A is 0 and B is 1. Then the third possibility is for A to be 1, and for B to be 0. That's the third possible input, or third possible input combination. And the fourth possible input combination is for both inputs to be 1. So you cannot have any other digital inputs. There's no other combination you can make. It's either both are 0, either one of them is 1, or both of them are 1. So there are four maximum possible input combinations for a digital for two digital inputs into a digital circuit, a digital logical circuit, or a digital circuit basically, or logic or combination logic circuit. So if you have just two inputs to your digital circuit or your logic gate circuit, yeah, if you have just two inputs, then it means that the combination of those two inputs have four possibilities. Either both inputs are 0, or one of them is 0 and the other one is 1, or the other one is 1 and the second one is 0, or both of them are 1s. So these are the four total possible input combinations if you have two inputs to your digital circuit or to your logic gate circuit. So let us let us actually label our inputs, and let's label the terminals of our AND gate. A inputs A. So let's see where we'll move input A to. So let's bring input A here. Let's make this A, input A, and then Control C, Control V, replicate our A, delete the A, change it to B. And that's that about that. Control V, paste again, delete, change it to C. Let's drag out a bit. Okay, yeah. So we have two inputs, input A and input B, and we have one output, output C. Two inputs and one output. So let's try and determine what the output of our small logic gate circuit will be. So, and the truth table for an AND, or for an AND gate, the truth table for an AND gate. Truth table for an AND gate. Then 0. Now when both inputs are 0, what would the output be? So you have to determine that. So we can run a little simulation to see what will happen if both inputs are 0. What would the output be? If one input is 0 and the other one is 1, what would the output be? If one input is 1 and the other one is 0, what would the output be? If both inputs are 1, what would the output be? So normally if you are in a physical laboratory, you can run this experiment and you determine yourself what the output C will be for all the corresponding inputs of A and B. But this is a virtual laboratory, we can also do that. So we will spend the rest of today's module or today's lecture determining the corresponding outputs for various inputs to a logic circuit. So let's see. So A and B, now we need to determine what exactly is our input. Let's determine our input. So now we want to feed in our input. Yeah, that's it. Logic gate input. So if you click and drag logic gate input and output, that's input there. Click and drag, or you just click alone and click and place, one of the two. Click and place, click and place, or click and drag. Either of the two works. So let's shift our B down a bit, go to the edge, let the cursor change. Yeah, let's move it there. Click to the edge, click again, go to the edge, let the cursor change, drag. So that's A and B. Let's see if we can move this down a little bit. Click and drag. Okay, and logic output. So click, drag, connect. Oh, sorry. Let's move the C. Let's see if we can move the C. Move it. Yeah. Click, connect, click, drag, connect, click, drag, connect. Okay. So we've connected our inputs, digital inputs A and B, and we've connected our output. So let's simulate. Press F9 or you press this play button on the top. So we simulated. You see that the indicator of the digital output has changed color. So on our left tab, so we can actually, let's see, can we click? You're able to click on this. Okay, we can click on this. When you click on it and change to red, it means that is 1. When it changes to red, you are changing the input to 1. This is 1. This is 1. See that when we say 1 1, something happened to the output. You look again, this is 0. This is 0. So you can change on the left. You can change the output, so the voltage levels. Let's stop the simulation. Let me. I want to move. Let me move this A upward a bit. On the left tab, there are multiple views. You can view a normal output, or you can view voltage levels, or your current levels, or logic levels. That's on the left. On the left of your screen here, this left tab. So let's simulate again. Click. So when you're in voltage levels, you see that this is 1. A is 1 here now. A is 1. We see that this is supposed to be 5 volts, it's 9 volts. So it's a bug. It's supposed to be 5 volts. So whenever you see 9 volts in the digital circuit, especially in this environment, this live wire environment, just assume it is 5 volts. In actual fact, it's supposed to be 5 volts. That is a bug. So it's 0 volt now. See that when I click on it, it's 9 volts. That's 1. If I click on it again, that is 0 volts. So you can press to change the state. So this is 0. So this is logic 0 and 0 volts. Logic 0. So A and B are both 0 here. So A is 0, B is 0, like this. At this point, A and B are both 0. So if you click on it, it becomes 1. This is logic 1. Also 5 volt, not 9 volts. Ignore the 9 volts. So 5 volts, logic 1. When I press it, my input B becomes logic 1, or 5 volts, not 9 volts. And when I press it again, it's logic 0. So current flow, you can check the current flow as current is flowing from the input to the output. Let's ignore that. Logic level, this is what really concerns us. So you see that without pressing it, everything is at logic 0. A is 0, B is 0, C is 0. The inputs are both 0. If I click on it, it becomes logic 1. That when I was checking the voltage levels output, instead of 1, it was showing me 9 volts. But in the logic levels output, see 1 and 0. This is what really concerns us in this circuit. So when A and B are both 0, our C is 0. A is 0, B is 0, C is 0. So we can now fill up. We can fill up our truth table. We started by filling only the input. Now we can now fill the output of the truth table. A and B is the input of the truth table. C is the output of the truth table. So C is 0 when A and B are 0. We run the simulation to confirm that. So let's check. When B is 1, what happens? C still remains 0. So stop simulation. Go there, fill the truth table. C is 0. Run the simulation again. Run the simulation again. change only A to 1, C still remains 0. So you see here that C is 0, and then run the simulation again. When A and B are both 1, C changes to 1. So for an AND gate, the output is 1 only when all inputs are 1. When all inputs are 1 for an AND gate, that is only when the input will be 1. Else, the input will always be, the output of an AND gate will be 0 unless when all its inputs are 1. So the truth table basically helps us to understand the behavior of an AND gate. So we just run a mini experiment, a small experiment with one single AND gate. Um, they are real AND gates. When we get back to the laboratory, you'll make use of physical, real AND gates, real implemented AND gate, and you will see that the result will be the same. So let's go back to our standard gates. Let's go back to our logic gates, and I want you to know that with this video lecture, you can always, if you don't understand any part, you can always go back again, go back, or you can rewind and go back to any part of the lecture that you don't understand, and you can go through it again. So, in that way, it's easy for you not to miss out on any explanation. So, like I said, with toggle, you click, you can change it. You can change the inputs from 0 to 1 just by clicking on it, then run the simulation. So basically, we spend most of today's lecture on in the logic levels window. This is normal output on normal window. Um, so we can click delete. You can click on the wire and delete. You want to change the gate, so you click on the wire and delete. You can click on it and delete. So I want to show you if this were to be in a real experiment, if you have to be in a laboratory, we don't have, you might not get, there's no terminal here. This virtual environment makes it simple, easy for us. We just have a terminal called input. So but in a real sense, in the real world, instead of terminal, we're going to actually have something like battery. You have a DC voltage supply. So if you want to generate logic 1 in real life, you need a battery, you need a DC voltage source, not just one terminal. So we could use one terminal here because it's a simulation. In the actual sense, in the real world, we will use a battery or a DC voltage source to generate our logic level 1 and logic level 0. So we've gotten two batteries out. Change the property. We want to change the voltage. We've said that logic 1 is 5 volts, not 9 volts. So we create our own 5 volts. Right click, change the properties, 5. Okay. So we've created two voltage sources, two DC voltage sources, which will serve as our digital signals. So you connect one end to one terminal, click and drag, click, click. To make a curve, you click again, click. So click, drag, click, 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 and connect. So we connect the negative terminals together. Let's check. You see, you connect the negative terminals together, the positive ones to the respective input A and B. You connect the two grounds together. Okay, we have to change this our gates. These gates don't respond to battery input. It's another bug on the live wire virtual library. We see here that it's X, so it's supposed to give us 1. Here it's giving X, which means that it doesn't recognize that 5 volts. It doesn't recognize the batteries at all. It doesn't recognize the battery. So we have to change. We have to change the hand gate. So this hand gate 4081V from LiveWire is not responding to the batteries like it ought to. So we need to check. We need to actually. It's only response to this input terminal here. Only if I put this input terminal here that's going to respond. So whereas in the real world, we don't have input terminal. What we have is batteries. This is voltage sources like 5 volts. So what we do now is that we select logic gate, go to integrated circuits 77,400 or 7400 series. So here we have AND gates models. We have gate models that behave very closely to real world gates. So 74LS08 is an actual IC. You can buy this IC 74LS08. So it's a real IC it exists. So its behavior is as close as possible. It's closer to the real thing than the other one we use. The other one is basically it's it's less realistic in its behavior than this one. So let's connect 5. Let's use this one. So it's still the same AND gate. It's an AND gate. The behavior should be the same. It's an AND gate just like the other standard one, but just that this one responds to a 5 volt input like it ought to. So let's run simulation. Okay, sorry, I didn't connect the output. Connect the output, run the simulation, and let's check our logic levels output. Run. So we see here that 1, 1, and 1. But you see that at the C is giving us X. It means that the virtual output terminal or digital logic terminal does not respond to this 5 volts from our input. It's also not behaving like it should in a practical. So we have to delete another bug. We have to delete and replace it with something that will respond. So it's only if I made the input that logic terminal input, that was only when this output C will respond. It's supposed to actually light up, but it doesn't light up. So we will have to change it. Let me see if I can shift this guy up a little bit. Um, shift. So just click at the edge and drag up a little bit. Click and drag. Click and drag. So we need to change. We need to change the this um, output terminal. We have to change it to something that is more practical in nature. So let's see. We need output component, output component, output component. Yeah, that's it. So we can use a lamp like well. Let's use LED. LED, use LED for digital. The lamp we use that for AC the other time. Or it could also work for DC.